Okay, probably we can start. So welcome to your NPTEL tutorial session. So it is your week 3, and so this week there were topics on the angular momentum. So basically, you would have seen a lot of this orbital and spin angular momentum. Perhaps maybe in your last quantum mechanics course, which you have might have before. Before this advanced quantum mechanics course. So, but this time, you have a bit of review of that and some more things into it because that will lead into some more important topics of like nuclear magnetic resonance and your spin couplings and angular momentum, LS couplings and many more things that would be very important when you try to learn things in the context of atomic or molecular physics. So this was your topic more or less like for this week, like which you have questions mostly related to this topic on your assignment and even your assignment is live and I think uh, the due is still there, but yeah. So we'll discuss on some related problems today here. So so a little review again for what is angular momentum operator, how we see angular momentum in quantum mechanics, and right. So like yeah. So orbital angular momentum. This is what we will start with. And from your earlier notion of angular momentum, you would be already familiar like how we express angular momentum. So this is how something we write angular momentum. That is something uh, position vector and momentum. That is the cross product of position and momentum vectors. So, that is we know so far, like classically how we define angular momentum, and so its components can be given as Lx, Ly, Lz, how we have written here. So, like basically taking the cross product that gives you this. But again, now in quantum mechanics, so these are some vectors, and you need to promote it to be a operator this time. So now we will be treating this angular momentum vector so far, but we know already uh, some operator, and again we will have their own eigenstates uh, and yeah, some important things about this orbital angular momentum, like they have a very special kind of eigenstate. When you uh, write it in, when you write it in the form eigenfunction, so they would give you some form of spherical harmonics, and spherical harmonics, that is something very interesting. So once you have this angular momentum operators, so now you can write their corresponding angular momentum algebra. So that is basically the commutator algebra. So and this are something written like this. Commutator of Lx Ly gives you Lz with the prefactor of IH bar, and same way you have L by LZ angular momentum commutation, and then LZ LZ. So uh, and then you also see here that L square L or L square Ly or L square Lz, their computation is 0. So from here, like you can say, like I mean, this LXLY operators, like they do not commute with each other. So like it's something which you can say that like if you uh, can able to measure the angular momentum of along any direction or along any basis, then you cannot simultaneously measure the with arbitrary accuracy the angular momentum of its orthogonal basis. So what I mean, like you cannot simultaneously able to measure Lx and Ly with arbitrary accuracy. So, uh, but from the second line, like which I've written, the commutation relation of L square and Lx, or L square Ly or L square Lz, you will see that their commutation is zero. So from here you can say that like you can measure L square and Lx at the same time with arbitrary accuracy. So and it is the reason like you can see that like because this L square and Lx will eventually share a common eigenstate. So that eigenfunction is basically what I was talking about, spherical harmonics. So I think these are some things which we have already gone through. So uh, hello Mehdi, are you able to hear me? Hello, hello Mehdi, uh, are you able to hear? There was no one around here, so like I'm not sure like if my voice is properly like audible. Okay, like hope like it is clear to you people. I mean, I hope it is audible. So yeah, I was talking about this. Uh, I was talking about this angular momentum operators and their eigenfunctions. So like as I said, like this. LXLY commutation like is they do not commute with each other and but if you see the commutation of L square and Lx or L square Ly or L square Lz, like they do obey this commutation. I mean they commute with each other, and that's why like they can share a common uh, eigenfunction or eigenstate. So in the uh, the algebraic form, like we can express this eigenstate relation as something like this. So when L square acts on this Lm, so Lm are basically the eigenstate of this L square and of uh, and Lz as well, because uh, they again have the same eigenstates. So right. So this like eigenfunctions are basically yeah, like this eigenfunctions like why we do not with L and N. Again, I hope like you have seen it already from your previous course, or maybe even like this time like it would be again explained well by your professor in your lectures. So because we know like this Lm are basically the two independent quantum numbers are the two quantum numbers by which you would describe your angular momentum state. So L basically I mean like we'll see that again. Like I mean I have written the form of spherical harmonies. Basically from there you get that. So like it is something like if you do like quantum mechanics in 3D in three-dimensional system, like you would have three kinds of like angular momentum, three kinds of quantum numbers, n and m. So and those three quantum numbers, like they basically like out of those three quantum numbers, L and M are basically your angular momentum quantum numbers, and they comes from the spherical harmonics. And again, we need to make sure that if that system, that three dimensional system which we are talking about, is spherically symmetric. So for a spherically symmetric three-dimensional quantum system, we can always express this their angular momentum eigenstates by this. Uh, so uh, Angular momentum eigenstate in three-dimensional spherically symmetric quantum system. So further, now we can express this Lx, Ly, Lz operators, like whatever like I was showing at the beginning. Like it is the generic way how we write this Lx, Ly, Lz. But now if we write in terms of spherical coordinates, so like this is how the form it would take. So I have given this right here. So we have to do this coordinate transformation, then we'll get all the forms of this angular momentum operators. And then this is what I was telling you, this spherical coordinate like basis, you will have this Lm, this eigenstates as some uh, eigen as some kind of eigenfunction in variable theta and phi. So theta and phi are your angular variables. So and this ylm theta phi is basically uh, finally something is given in this form. This is a pretty big expression, so that is how we write it. So uh, the uh, the factor which is there within square root is something like which controls the normalization of this ylm theta phi eigenfunction. So ylm theta phi is uh, orthonormal eigenfunction. So that means if you take any different ylm, so I mean what I mean, so if you take ylm theta phi with some other yl prime m prime theta phi, uh, like d omega. So so mm, like the like that will be your some delta L minus L prime and delta M minus M prime, or basically LL prime, FM prime. So something which you know already, that like this the delta uh, this deltas are something represents orthonormality, or basically like for orthogonal relations. So ylm is normalized, so that's why you can see a square root factor hanging over here. That is what your normalizing factor. And this L and M are the quantum numbers which I was talking about. Like this is what you have for a uh, like for a spherical symmetric quantum system, for a spherical symmetric three-dimensional quantum system. So this is the complete. Uh, okay, so was there a question like Mehdi? I see your hand was raised.
Hello,
Yeah, yeah, yeah,
can you hear me?
yeah, yeah.
I just want to know that in the spherical harmonics function, what
Uh,
is the form of this PLM? That means cos theta. Is it a Legendre function or Laguerre? What kind of polynomial is this?
Oh, so this PLM cos theta. So this is a associated legendary polynomial. So let me write this. So this, I mean, uh, associated legendary polynomial. So I hope like you have seen this legendary polynomial, like
Okay.
we write it as PLX.
Hmm.
So so those are basically this similar. I mean, that is the same legendary polynomial, but you have a different argument. You work on this theta coordinate, so that's where you have something PL cos theta. So these are called as an associated legendary polynomial, not
Okay.
exactly legendary polynomial, but associated legendary polynomial.
Okay. Thank you.
So this was your
Yes.
what
Yes.
you
Yes.
okay. So
Thank you.
yeah, so for m greater than zero, so you basically have this form, and for m less than zero, you have a different form. There you have this PL magnitude m cos theta. That is your different form of associated Legendre polynomial. So this is a very big expression that comes at the end for a when you solve this for I mean, this is basically you will get this when you start from the beginning. So like when you start you give a potential, a spherically symmetric potential, spherically symmetric potential, like something v of r, and you give that potential in the Schrodinger equation, and then you go on to solve that Schrodinger equation, and like you solve it by using some methods of separating variables, and you assume some, like for example, I'm talking about hydrogen atom, so that is a spherically symmetric system. So the potential is basically like something which falls over 1 by r, so which is independent of any theta and phi. So you can take that as some spherically symmetric potential, and in it you will get some that psi is some solution for that Schrodinger equation, and that is something would be given like this r, and some r and violin theta r. So so this is the radial part of your system, and this is your angular part. This is a radial eigenfunction, and that this is your angular eigenfunction. So, and this angular eigenfunction is basically the eigenfunction of angular momentum, and yeah, right, and yeah, that is how you solve for your hydrogen atom system. So now, in the same, okay, there's one more
Hello.
question. Yeah.
So you say the wave function is a combination of the radial and the angular part.
Right,
So
right. So for like
in
if
this
you have a
in
hydrogen
this
atom system,
so my question is, in this angular part, you still didn't include this spin, yeah? It is only for orbital angular momentum. These spherical harmonics.
right, right. It is for only orbital angular momentum.
Okay.
So,
Okay.
like for example, when we are talking about hydrogen atom, so we know like a hydrogen atom, like a nucleus is sitting at the center and a electron going around it. So we are talking about the angular moment of the electron, which is going around the nucleus. So that is basically the orbital angular momentum. So
Okay.
so we are now I'm talking about a new angular momentum, that is spin angular momentum. Again, you would have seen that in your lectures. So that is again explained well by the professor. But this is again a small review that what I wanted to say is like the way you have angular momentum, orbital angular momentum, the way you are denoting angular momentum operators and their eigenstats in the same context. We can do the same uh, algebra for this spin angular momentum. So it is because their algebra is similar, because here also we know, from the beginning, like if you would have seen from Stern-Jalak experiment, where everything started, the idea of intrinsic quantity of any quantum particle, and that is spin. So So when you take this quantity, the spin vector or the spin operator, and it also has three components: Sx, Sy, and Sj, and even there, uh, algebra is also very similar to what to the algebra what you have for the anglo orbital anglo momentum. So in the same spirit, like we can draw a similar construction for the eigenstates and the eigenstate relation in the same way. So this is like how you would see for uh, spin angular momentum. So this is just something written in the same way like how orbital angular momentum is written, and, and this is for the estate for the uh, there will be H bar over here. So yeah, so this is the anglo y again s square and sz have the same eigen state because they again commute here. So the algebra is very similar, very same. I mean, is something you can say. It is basically the same thing what you had for orbital angular momentum. So this all this algebra will stand for spin angular momentum as well. So that's why you can also like express their eigenstate in terms of two quantum numbers, that is s and ms, instead of what we call for L and M for orbital angular momentum. But there is a very clear subtle difference between both orbital angular momentum and spin angular momentum. Although their algebra is very same, but mathematically, if you would see the mathematical structure, they are very different. So, like, I think maybe when you go to your like a complete like higher, I mean, math course or mathematical methods course, like you will see that, like, I mean, you express angular momentum like algebra, like the LX, LY, LZ, like they like you would see like these are basically some generators in SO3 uh, group. And if you would see, if you are talking about the spin angular momentums, the spin basically belongs to this SU2 uh, group. So these are basically the generators for the SU2. So like these terms are, if you are not familiar, like this group theory methods, like you would maybe see that in future, like but there is a very clear difference that I wanted to like. I mean, I wanted to emphasize that like they are not the same after all at the end of the day, but their algebra falls on same footing somehow. That's why we can able to express their eigenstates in the same spirit. Uh, so yeah. So moving on, like so like like I think like you have gone through like some kind of, I mean, this orbital angular momentum, spin angular momentum lectures, like uh, right? Didn't you? Yeah.
Yes, yes.
Okay, you have studied them, or like, or you have looking this for the first time, like
No, I have studied some, but not full. But I have
okay,
a
okay.
concept about this.
But you have you know that like this is already there in your course. I mean, already there in your lectures videos.
Yes, yes.
Okay.
But
Uh, yeah.
I think it is my advice that you do it. It is very perfect. You are describing very well. But I will always say that at the end of the day, just explain one sentence or two sentences, the physical meaning, so that it will be understandable.
Okay.
Because
Physical meaning
just
of like what
of
I
like
mean.
say you are measuring the spin
Uh,
and
uh,
you're getting it is quantized in the z direction. You're getting s squared divided by 2 minus s squared divided by 2. So just give some common such as that how the spin orientation can due to the magnetic field it can orient, something like this. Just a physical meaning that how it works.
So you're talking about like a more detail on some spin of.
Not two more details
Mhm.
like that. You clear the, for example, you retain the angular wave function. So here you're clearly explaining every part, that this part is corresponding to a straight linear function, this part is the phase, so something like this, so that I can understand the equation.
So you mean like so basically you're talking about this YLM function. So that is what you want me to explain better.
No, no, no. I have already understand it,
Okay, okay.
because you say that this is every part. You are saying that this
Mm.
is linear function, this is phase
Mm.
change,
Mm.
and this is the constant term. So this way,
Mm.
so that I can get some what is actually happening here.
Okay, like this YLM part, no,
Yes, yes, it is clear. It is clear. Then go on. It's
is
okay.
clear. Okay.
Okay. Yes, yes.
Now, if like I mean, you were talking about some like physical meaning, like the physical meaning of YLM or something. What you want to know?
No. So, for example, you are calculating something, and at the end you get some results.
Okay.
So you can say that if there is necessary, if there is necessary to tell something that it is understandable more
Okay.
clearly.
So you are telling like if there is something necessary, if I missed it, then I should tell.
Yes, yes.
Okay.
Something.
Okay. Okay. So like first of all, I'm just giving a very brief review. So like
Yeah, it's okay. It's okay. It's
the
okay.
main
Yes.
thing like is I will be going through the problems. But anyways,
Okay.
like
Okay.
you are like welcome to ask any questions. But
Okay.
like I can go through as much as detail you want me to
No.
go through. There is no problem. So like the reason like I have given only very few things right, I have written here. There are lot of details. You will find it in your books or in thoroughly in your lectures. So
Okay.
like the reason why I have given very brief amount here is because I will be focusing more on problems. But anyway, like if you want me to discuss more on this, like I'm happy to do that. But
Okay.
yeah,
No
so
problem. Okay.
yeah, like if I can tell you more about this thing, like even little more short way, then like this while and theta phi, like these are
For ex-
yeah.
for example, you said that LX, LY, and LZ, the angular part is a group
Hmm.
of SO3 group,
Yeah, 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 yeah.
and also the spin is a SO2 group. Actually, I didn't know this information. That's why I
Okay,
said if we have some more information, then it is
okay,
good.
okay, okay, okay. Right, right. Yeah. So yeah, like we'll try. Yeah, I will try
Okay.
to like give as much as like additional thing if that is coming to my mind. I will definitely
Okay. Okay.
share.
Okay. Okay. It's okay.
Yeah,
Okay. Thank you.
yeah. But here like I was like giving you a very short description what this ylm and this eigenfunctions are. So like as I said, like this ylm you can get it like when you solve for hydrogen atom system. So like from Schrodinger equation you uh, basically get this psi and lm solutions. This is something first you assume that this psi and lm is some radial function times some angular part. So yeah, this is 5. uh, so this was I was talking about. So like this ylm basically is your uh, angular part of the three-dimensional quantum system which you are trying to solve for, and this ylm is something you get like as I said, like this is some normalizing constant, and this is the theta dependent part which is your associated Rosenthal polynomial, and this is your phi part. Like this is something simply like a kind of phase factor. You have exponential of I and phi. So these are theta and phi dependent part of your solution of for the hydrogen atom system if you are considering, or something like spherical symmetric potential like this V of r. And the radial part is something this R of r, which is like we will solve it from the like from a different separated differential equation, like that you would get that in the mathematics of hydrogen atom problem. So like if you go into that, like you will understand more about it. uh, so and yeah, same way like I was talking about spin angular momentum, and yeah, as you said, like uh, uh, I'm writing this spin angular momentum algebra in the same way. I mean, their eigenstate relation in the same way as I wrote it for orbital angular momentum, because they share uh, a common form of algebra. But after all, at the end of the day, they are not really the same thing. if you would see the exact mathematical structure, they differ a lot. That like this Lx, Ly, Lz, they are basically the generators for this SO3 group, and X, Y, X, Z are the generators for SU2 group. So, like this is something, if you want to know in more detail, you need to learn a little bit about of group theory. So, which I think you would, I mean, maybe you would read it in the future, or some group theory mathematical method courses available around you. You can take that. So that was the thing like I was talking about, and like moving on to the problem. So like, is there anything more like you want to ask, like, or is it fine?
No, it's okay. It is fine.
Okay, okay. So uh, we can start like working out this competition relation. So like the first is yeah, this is LZ. It's just a quick exercise how we can write this, how we can prove this computation. So a computation of LXLY. So how can we do that? You have the form of LXLY as I showed you at the beginning. So these are basically your LX and LY. So you write them. So yeah, Y PX. Uh, it's not YP, so it's YPZ. YPZ, then ZPY. Uh, we are doing this comparison of Lx with Ly, so Ly is Z Px minus X Pz, and so now solve it term by term. uh, Z Px, then you have minus Z Py, uh, Z Px, then minus Ypz, X Pz, and at last you have Z Py, X Pz. So right. So here, like you can see, I mean, from the Heisenberg uncertainty relation, you are already familiar. Like uh, you know this X when comes with Px. So these are basically your canonical variables. So is IH bar. So this x, px are canonical variables, canonical conjugate variables of each other. Same way y, py, and z, pz. So this is your, I mean the Heisenberg uncertainty relation. So using this, basically you can show this. I mean, you can work out from here. So the first term you have pz and z. So here you can see that like if pz and z is appearing in this computation, then somehow you would use the Heisenberg uncertainty z pz commutator relation, which is IH bar. So like, and you have y and px. So and you know that when y commutes with px, I mean, their commutation is zero. That means y and px, they basically commute with each other. So they are not canonically conjugate variables to each other. So Since you know like y px, like do not commute with each other, or basically like what I can write the first term is something y. I can take a overall y factor outside the commutation, and ez z, and same way I would take out the px on the right hand side of that commutation. So inside I have pz and z, and the same thing like I can uh, so here like in this part like you would see that like uh, here you have py and z. So py and z is again something like uh, they commute with each other, just like how I said like y and px commute with each other. So same way z and py, they also compete with each other. So the second term like would be like would give you zero, because again if I pull out z from the left and px from the right, so within the commutation you will have p by z, that is zero, and same way like pz and x also like commutes with each other, like that will also be zero, and at the end you have this last term, uh, and this one, right, you can write here you can see that you have z and pz appearing again once more, and then py and x is there, but they commute with each other, their commutation is basically zero. So again I can write this term something x uh, pz, uh, or yeah, let me write. I I'm first changing the order, and so you have so I have changed the order, so that's why this positive become negative, because when you change the order of the commutation, I mean if the commutator of a b is given, when you change the commutator to b a instead of a b, then a negative sign will be picked up. So that is this. So basically what I mean, like uh, like commutator of a b is basically equal to negative of commutator of b a. So since uh, a b b a, so here again like so the commutator of pz and z is we know, like as I said, like from Heisenberg uncertainty, we know z pz is ih bar. So the commutator of uh, pz would be negative of ih bar. So px, and for the last term you can do again like x pz z py. So uh, so from here like you will have uh, IH bar, like I am taking this common factor outside, because this will also give you minus IH bar, and uh, then inside you will have x dy uh, minus ypx, and that is nothing but your LZ operator. So this is how like straightforward you can show this commutation relation for LXLY becoming IH bar LJ. So yeah, did you like get this part or any
Yes, yes.
doubts?
Okay, okay.
Okay, so next again we have. another commutation to prove. This time we have LZ and L plus. So now what is L plus? So L plus, like you, this is your ladder operator. We call this L plus as a ladder operator. This is something very similar to the ladder operators you have for harmonic oscillator. So I hope like you are aware of this harmonic oscillator ladder operators. Like we saw this. I mean, even we discussed in our last week discussions, like I mean about this harmonic oscillator ladder operators very often, and they basically help you to go to the state above the state which you are working, or they would help you to go below the state which you are working. So they basically they can raise a state upon acting the raising operator. They would lower the state upon acting the lowering operator. So and here also in angular momentum you have this L plus L by L plus L minus operator. So L plus is basically your raising operator. So that is defined this way, and same you have a lowering operator that is defined in this way. So their function is very same as what I was talking about, the harmonic oscillator ladder operators. So if you have some kind of this step, then you will have like some I mean, yeah, I mean what I mean, like that is basically equal to some constant, some factor, L m minus m plus 1. So they will take to L m plus 1. So if you have something like L is, let's say L is something 3, and m is 2. So if you are acting L plus on state 3 2, then that will uh, take you to 3 3. So, and right. So that is what L plus and L minus will do. L minus will lower it down. So uh,
Uh,
yeah,
so in the ladder operator, we have
right.
written that
Uh,
L plus when
mm,
it's acting on Lm, it is giving me Lm plus 1. So in the angular momentum subspace, the norm L is conserved, but the associated quantum number is increasing. Yes,
like sorry, oh, what is concept? Like
the angular momentum, the total angular momentum L is conserved.
uh,
Sorry, not total the orbital angular momentum L is conserved, but it is quantizing in the uh, m, that means m plus 1.
uh,
So
uh,
because it is just changing, the L is just changing, only the associate quantum number is changing.
I mean, like could you repeat the question? Like I couldn't get it. Sorry.
Say, uh, just say when you want to measure the angular momentum,
Mm.
you act L square.
Right,
That is
L
the
square.
angular momentum
Yeah, yeah,
operator.
yeah.
Hello.
So we operate L square
So
to get the
L square to Lm, then we get the value is L into L plus 1 into S square square.
right,
This is
right.
the argument.
Yeah.
Yeah.
So this is
So
that is the eigenvalue. So that is what the
eigenvalue.
value
So
you will get.
yes. So here the eigenvalue is the changing. Only the associate quantum number M is changing.
Here the oh, you are telling like so when we operate L square, like you mean like when I am operating L square on
Yes.
Lm,
Yes.
so I
Yes.
get something L of L plus 1 h bar square,
Mhm.
L plus m back again. But
Okay.
now when I'm operating like this L plus on Lm, so I get some square root factor which I don't remember now. So with that square root factor, you will get L plus L m plus 1. So you are telling this m is changing right now. So why is it
Yes.
so?
Yes. 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 Yes.
Yeah, yeah. So first of all, like this is not a eigen-state relation. You remember that, like you note this. This is uh, not a eigenstate relation. So because this L plus the I mean inherently these L plus operators are basically designed to raise your angular momentum state. So for example, if you have any quantum particle, if you have like in hydrogen atom, if you have some state, let's say like uh, some 3 by 2, that is your LM state. uh, if you operate L square on this 3 by 2, like you get something like uh, so 3 plus 4, so 3 times 4, that is something 12 square square 3 2. but but if you operate L plus on 3 by 2, so you will get some number again, and then it will go to 3 3. So it basically takes you to the state above this 3 2. So that is the work of L plus operators. That is what how we have purposefully constructed this L plus, because this L plus and L minus, they are very useful when for various like mathematical calculations, and we have reasons for that, like how like what is the significance of this raising and loud operators, like that would be there everywhere, like when you do like this quantum mechanics, the advanced quantum mechanics, or even when you do field theories or whatever, like these are some like the primary tools. So ladder operators basically like whichever basis you are working on, and in that same basis, so basis I mean like you, this is your eigenstate basis, LM basis, or you are in harmonic oscillator, like in harmonic oscillator you have n basis, that is your the quanta state, like the uh, like n equals to 0, that is your ground state, and equals to 1 is your first excited
So,
state. So there
for
also
ex-
you have a and a dagger operators, so that also helps you to raise and lower this this uh, eigenstates. Yeah, like
so
you.
for example, your LM state is 3 3.
uh,
So if you operate L dagger on that, then it will change because this is the maximum state you can
yeah, yeah.
raise.
Now what happens when you operate this L plus on this 3 3, so this will be 0,
Okay, thank you.
because there is no other state above it. So
Okay,
like it cannot go any further up, because that is the total
limit.
size of your basis. That is your, like in the that Hilbert space itself is very small. So like
Uh,
you have 3 3 3 2, then 3 1 3 0, and till 3 minus 3. So that is the, and so above and below it cannot go. So same way, like if you operate L minus on 3 minus 3, so that also will give you 0,
okay, thank you.
because there is no state. Yeah. Yeah, so that was about this ladder operators. So in this question, like I had this like to show this commutation of this LZ with L plus operator. So as I said, like this L plus and L minus, they are defined this way, this ladder operators. Now to prove the commutation relation, like LZ and L plus, so you have LZ, and L plus is Lx plus ILy, Lx plus ILy. So that is Lz Lx plus I Lz Ly. So now, yeah. So from here, like you can see that like uh, Lz Lx, like as I showed you at the beginning, like these are the commutation relation. So LZLX, you have IH per LY, and uh, IH per LY, and this one you have LZLY. That will be your I think minus IH per LX, and So that is IH bar Ly. So iota times iota is basically minus one, and negative sign is already here. So that would be like overall you will get a positive sign, and h bar Lx, and that is h bar Lx plus I Ly, and this is the same L plus you got it. So yeah, that is the commutation how you can prove for LZL plus giving you H bar L plus. So like same way, like you can also see there is one more commutation like minus H bar L minus. So now you will use L minus is Lx minus I L1. So yeah, so that is how you can prove this. So you did you get this?
Yes.
Okay, so and last we have this one more commutation. So this is L square plus L plus is 0. So now L square, like how you can write it. So yeah, L square means yeah, L square with L plus. So that is Lx plus ILy. So that is L square Lx plus I L square Ly. Uh, yeah. So again, at the beginning, as I showed you, like L square comes with Lx, and even L square will also come with Ly. So that is you get 0. So that is what the commutation relation I showed you at the beginning, because they commute with each other. They share the same eigen function. Yeah. So like, so any questions or any doubt here, or all the computations like
Okay. Okay.
wait.
Yes. Okay.
Okay. So next, like we have this letter operators once more. Uh, so uh, so this letter operators, as I was telling, so uh, that is something defined this way, and so and in terms of like theta phi, these operators are given by this definition, or basically you can also like see it how this basically expression will reduce to. Uh, at the beginning, I showed you this. This is Lx and Ly Lz. So we know L plus is Lx plus I times Ly. So you can use this form of Lx Ly in terms of theta and phi. And yeah, so when you do a little bit of this small algebra, you will get this. The final form of L plus would be this, or L minus. So now what is given here? So this L plus L minus, the operator form is given in terms of theta and phi variables. The action of this and the action of Lz operator on spherical harmony, that is YLM. So YLM theta phi on spherical harmonic basis, that is uh, yeah. So let's say this is denoted like this, uh, YLM. So so when M is equal to L, so you basically have this YLL. So and again, like as I was like telling you before, like when you add this L plus on YLL, so LL is the highest and it cannot go further, so that is you get 0. So then you determine what is uh, So you have to determine this YLL theta phi. So like the spherical harmonic, like which I was showing with the general form, but now we have to specifically show this how we can calculate the spherical harmonics for this YLL theta phi when these things are given to the L plus L minus form and the action of LZ on this YLL state and L plus the action of L plus and YLL is 0. So with this information, so now what you can do, so we have LZ acting on YLN is H bar L YL. So that is uh, good, and that is what given to you. And the LZ form and the LZ operator is also I have showed you at the beginning. So this is the form of LZ. So using this LZ form, so minus I H bar del by del phi y ln is H bar L y ln. So that is what I can write. So from here, like I can write this differential equation like this: I by L L, and since like we can see like even the expression which I showed you for YLL, it had one normalization factor and the Legendre polynomial, and then uh, you had this exponential of I m phi. So like what I was telling you, YLM at the beginning, which I was showing you, like it had some normalization factor, some square root term, then ELM, this theta, PLM cos theta, and then you have IM phi. That is the phi part of the YLM solution. So what I'm saying, like I can uh, in this differential equation also you can write this phi and the theta part separately. Uh, that is like I can write YLN as some theta. So the normalization is also contained in this f of theta with e to the power uh, I alpha. So this m is right now L, so L equals to m. So yeah, so now like we will explicitly see how uh, like how this f of theta like can be further determined. So and that for that we will use L plus is phi LL is 0, that is uh, L plus is already given to you in the uh, question right here. So using this L plus, uh, we can show uh, as per E I phi del by del theta plus I cot theta del by del phi acting on f of theta EIL phi. So since L equal to M, so it would be e to the power IL phi, like the IM phi which we are writing here. So that is e to the power IL phi. And so when this entire L plus acts on this YLL, so it gives you 0. So yeah, so you can write that differential equation again. So now like since like this I have separated what is like in this, like since f of theta is explicitly only a function of theta, there is no phi in it. So when this derivative operator del by del theta, when x on f of theta, I can just simply write it as df by d theta by replacing with ordinary derivative instead of writing partial derivative. So I can write df by d theta, uh, and since uh, this del by del theta will not operate on e to the power al phi, so now I can go to the next term. It's the same way I can write if uh, I f that is f of theta, and cot theta is there, and when you operate del over del phi on e to the power il phi, you get il e to the power il phi. Right. So that is equals to 0. So and from here, like you can solve what is f here, solve this differential equation for f. So basically you have the differential equation df d theta equal to l cot theta f, or you can write df by f equal to l cot theta d theta, and now just integrate that df by f equal to l uh, cot theta d theta, and that is you will get logarithm of f with L logarithm of sine theta. So that is the integration of cot theta with respect to d theta, and with some with some integration constant. So yeah, and so from here, like I can write further, like I can also uh, simplify further, like since this L is there, like I can write it as some uh, so this is from logarithm property. I can take this factor as some power, the argument of logarithm. Uh, yeah, um, plus this constant, then this logarithm of f by sine L theta is some constant. Let's say this constant is some r, or some k. Uh, so this f is uh, so this f of theta is finally some k sine L theta, or like you will have a different constant this time. So let's say k prime or k tilde. Yeah. So this is your f of theta, and then finally you can write your complete form of YLL. So that is YLL theta phi is a e to the power I L phi. Let me write some, yeah, this constant I'm calling it as k tilde I L phi sine 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 L theta. Yeah. So this is how you will get for the explicit form of YL theta phi. So this k tilde is basically your normalization normalization factor. Yeah. So did you get this part?
Yes.
Okay. So now, like, we can go to the next question. So
Hello.
yeah,
So in the calculation, like,
yeah, yeah.
you say um, when we are writing the theta equation, df divided by
Theta
d,
equation.
it is here, right? So
So df by d
but
theta, right?
df by d theta is equal to L cot theta f. So
Yeah, yeah,
where
yeah.
does that EL phi goes? In the previous line, there with one EL phi, e to the power IL phi.
Oh, okay. So there was yeah, there was this e to the power il5. Okay, yeah, yeah, right. Uh, so like I missed a el5 also right here. So that is why like I was like up to overall factor I was not
Okay,
taking
okay,
them. So
okay,
now
that's good.
this will be.
Mm.
So basically, you just uh, you
Yes,
leave
yes.
out this h bar I-phi, you operate this
Mm-hmm.
part with the
Now it's clear. Okay,
okay,
no problem.
yeah,
Yes, it's okay.
okay. Okay. So next, like we have this question problem here. So yeah, for a spin-off particle placed in a magnetic field B, the Hamiltonian is H minus gamma Sy. So this is Sy. Sy operator is here. So this is your the y component of your spin angular momentum. So that is what the I mean your Hamiltonian is described here. So where Sy is the y component of your spin operator. The state of the system at time t equals to zero was this, and uh, so uh, this basically denotes the like we are doing for a spin half particle. So for a spin half particle, this plus state basically denotes half and half. So this is your S and this is your MS. So and that is given as this. I mean, if your state is something SMS, then that is the eigen state of the spin operator or S Z operator. I mean, and also for S square operator. So that's why you can write SZ acting on plus minus will give you h bar by 2 plus minus. So that is basically writing SZ SMS is uh, MS h bar SMS. So you have plus half, you will get plus h bar by 2, and if you have plus half minus half, then you will have so like this minus state denotes half minus half. So when uh, SZ acts on plus half, then you get plus h bar by 2 and plus half, and when SZ acts on plus half minus half, then you get minus h bar by 2 uh, plus half minus half. So that is what like how this spin states are written spin operators, and the finally what has been asked here, like you have to calculate the probability of getting the value minus h pi by 2 when you measure the z component of the spin. So you have to after some time t, so you have to get like what is the probability uh, when you measure your SZ. When you measure SZ operator, that means when you are trying to measure the spin of your quantum particle, which is in this Hamiltonian. which is this Hamiltonian. After some time t, so you will get some. So each time you measure after some time t and some arbitrary time t, like you will get some value. So you will have, after some repeated measurements, you will have some outcomes. So based on the outcomes, like you will like you will tell what is your probability of getting one outcome, and you can compare it with other outcomes. So the comparison is basically done with the probability. So that's why probability is very important at the end of the any exercise. So when you are measuring SZ operator, so here too, like we need to know what is the probability of getting minus S per bit. So how we can start with this. So first, we you should know that like this Hamiltonian is given as something minus omega s1, right? So uh, for sy, like since we are working for a spin half particle, there are some more information like you need to know, or that has been like discussed with you before as well during the lectures, or if not, like I can tell you quickly. For spin off particles, like we have a representation. What I mean, the operators that we write sx, xy, xz, so you can always write these operators in terms of some matrix form. So like from matrix form, this is a very uh, trivial exercise which you can do it for a spin-up system. So let me write. So these are basically uh, Pauli matrices. SZ is given as square by 2, 1 0 0 minus 1. Yeah. So now, like when we write uh, half minus half, or half the SMS state. So you should know that like this eigenstates basically uh, denotes the eigenstate of operator, only SZ
Hello.
operator, not. Yeah.
So you're trying to write the eigenstates, spin eigenstate in terms of the Pauli matrix, in superposition, in terms of the superposition of the Pauli matrix.
I can you want to write eigenstate in terms of superposition of polymatrices.
Yes, you're trying to write now. Yes.
No, no, no. What I'm trying to tell you, we have to calculate probability at the end. So that is what asked in the question. So to calculate probability, I know, like to calculate probability, like we do some like inner product. Like let's say
Okay.
I want to calculate some. I have some psi and some a linear combination C1 phi 1 plus C2 phi 2. I want to calculate like what is the probability of getting, let's say phi 1 or some eigenvalue corresponding to phi 1. Then that probability is calculated as something phi 1 psi. We take the inner product and we take maybe this modulo square that will give us the probability. So here what is happening, like we also need to calculate the probability. So but we need to calculate in some eigenstates. So this phi 1 phi 2 are generally the eigenstates. So that is what I'm trying to show you. So the eigenstates that we normally we are studying so far here for SZ operator. So that is what denoted as SMS. So they remember, these are only the eigenstate of only SZ operator, not SXX1. So if you know, like this is your 2 by 2 matrix, if you would calculate the I mean the eigenvectors and eigenvalues for this SZ matrix, you will get the, let's say, the eigenvalues I am denoting as lambda. So you will get plus S bar by 2 and minus S bar by 2, and say, let's say the eigenstates. Uh, I'm denoting as psi. That is given as 1 0 and 0 1. So these are the eigenstates and eigenvalues. So eigenvalues and or eigenvectors, eigenvectors. So for this uh, sz operator. So same way, like you also have uh, for eigenvalue of Sx, if you would calculate, you will get plus h bar by 2 and minus h bar by 2 and psi of Sx. So this is uh, your eigenvectors. So that is given as 1 by root 2 1 1 and 1 by root 2 1 minus 1. So same way if you would calculate for Sy, you will get h bar by 2 and minus h bar by 2 psi will be the, I mean, eigenvectors for your Sy operator. So again, solve for the eigenvalues and eigenvectors of Sy. You will get h bar by 2 minus h bar by 2 as the eigenvalue, and Sy will be 1 by root 2, 1 iota, then 1 by root 2, 1 minus I. So yeah, let me get some space right here. So uh, yeah, so uh, uh, this is what the eigenvalues and eigenvectors which we need to solve this. Uh, I mean, which we ultimately need for the calculation of probability. So now, like I can, since the Hamiltonian, which is given, so the Hamiltonian is given right here. It is minus omega sy. So the Hamiltonian is in your sy basis. So the eigenstate, like which is given in your Hamiltonian, would be belonging to sy, because that is omega sy is your form of Hamiltonian. If it would have been sz, then you would have used this SMS eigenstate. Then by naturally the eigenstate would be 100. But instead of that, like you have minus omega sy, so your eigenstate would be this and this for the Hamiltonian that you are working on. So this is your eigenstate of your Hamiltonian with this omega factor. So so now, like at uh, psi t equals to 0, you have plus z. That means uh, plus, as I said, like this is your half uh, half state for spin of particle, and this is your eigenstate of S z, but not the eigenstate of Sy. So like I can write it as some linear combination of C1 phi 1 plus C2 phi 2, where uh, yeah. So this, yeah, this plus state which I was telling. So this is your up state, which is the eigenstate of Sz. So that is 1 0, uh, and the minus state would be 0 1. So now, like what I was trying to show here, this plus state is basically the initial state. So that means if the initial state is plus, I mean, if your Hamiltonian is omega sy, and the initial state of the Hamiltonian is given to be something plus, that is plus means 1 0, because that is what uh, I mean, this is only plus half state. So, but 1 0 is not the eigenstate of Sy, the Sy which is there in the Hamilton. So you can say if initially the state was in this plus state, then that means initially your state was not a eigenstate. Instead, initially your state was some linear superposition of eigenstate of Sy. So these are eigenstate of Sy. So like, are you like, did you get like what I'm trying to say here? So this uh, instead of S1.
Look,
Yeah,
but why at the initial why the eigenestate will be in the basis of SR? Because you're saying that this is plus a state, that means in the eigenstate of SZ. So it should be written in the superposition or linear combination of edges edged basis.
right. So like what I'm telling, so the Hamiltonian is given as h equals to omega sy. So the now tell me like what is the eigenstate of this Hamiltonian? Like eigenstate of this Hamiltonian will be in the
Is in the SY basis.
yeah for the S well. So its eigenstate would be either one like which I have written here. So one uh, iota or yeah, 1 by root 2 iota or 1 by root 2 1 minus I. So these two will be your eigenstates for the Hamiltonian, which is given in the question. So that is your eigenstate. So like and this is, let's say I'm denoting this one as phi 1, and this is what I'm denoting as phi 2.
Okay.
So so this is the eigenstate of your Hamilton, but in the question it is given initially your system was initially, that is t equal to 0, your system was uh, yeah, is in this state. Psi t equals to 0 is plus state, and plus state is your 1 0 state, which I have shown here, is the eigenstate of Sz, not Sy, remember.
Yes.
So psi t0 is plus is if psi t0 is 1 0 state, then this is not your eigenstate of Sy, not eigenstate of Sy. That means not eigenstate of Hamiltonian. So that means uh, your Hamiltonian is not in your. I mean, the initial state is not in the eigenstate of the Hamiltonian. That is what it
Yes.
means. The from here, like we can say, uh, the initial state is not in the eigenstate of Hamiltonian. Instead, the initial state plus will be some linear combination of eigenstate of Hamiltonian H or Sy. So so that means that plus has to be some linear combination of phi 1 plus C2 phi 2. So like did you get like why this will be linear combination? Like for example, let's say if you have a infinite well potential, like are you familiar with infinite well potential? Infinite well uh, like
Yes. Yes.
quantum
Yes.
system. So you know the in infinite well, like the eigenstates are denoted as something sine n by x by l. then sine pi x by L, or let's say like for harmonic oscillator, let's say for harmonic oscillator, you have the eigenstate as something n. So uh, 0 is ground state, uh, this is first excited state, and then you have second excited state, and so on. You have 0 1 2. So let's say if a harmonic oscillator is there, which is something omega a degree a, let's say this is the uh, harmonic oscillator, and its eigenstate, the eigenstate of this harmonic oscillator is n eigenstate, because the eigenstate of a degree a is also n. So if initially the harmonic oscillator is in some, I would say, is in some state psi t equals to 0, uh, could be some eigenstate, let's say something 3, or let's say something like some nth state psi t equal to 0. If let's say now, if the initial state of this harmonic oscillator is not in any eigenstate, then what would it be? It would be some linear combination of psi t equal to 0, some linear combination of c1 n1 c2 n2 c3 n3, and so on. It can be any linear combination of any number of eigenstates. So the same way, like here also I was telling you, the uh, if the initial state is not your eigenstate of the your Hamiltonian, then it would be the linear combination of the eigenstates of the Hamiltonian. So that is why I am writing this plus as some eigenstates of uh, uh, eigenstates of Sy, that is the Hamiltonian. So did you get like or still not clear?
Yes, yes, yes. So, Vasilo, due to the effect of the Hamiltonian,
Huh.
you're writing this in this way, yeah? It is all about the Hamiltonian.
Yeah, I mean, what I'm saying basically, like if the state which is like you have a state of a quantum particle, like let's say the quantum uh, system that you have, let's say harmonic oscillator, or any even the system which we are discussing right now, omega xy. So any Hamiltonian uh, is given to you, and if I'm asking like what is the state of the of your quantum system corresponding to your Hamiltonian h, so you will say like my system is in some eigenstate of the Hamiltonian, or is in some linear combination of its eigenstate. That is the
Okay.
two answer you can give, like only that is the possibility, that's the only two possibility. You would say either in any of one of the eigenstate, it could be in ground state, first excited state, or anything. So here in this Hamiltonian we have omega sy, so we have only two possibility, because we have two eigenstate of sy. One is 1 by root 2 1 iota, 1 by root 2 1 minus iota. Out of these two, none was in the initial state, because the initial state was something plus. So that means that plus is some linear combination of this 1 by root 2 1 1 and 1 by root 2 1 minus 7. Now is it clear?
Yes. So, is there any time evaluation here
Yeah, I
due to the
will do,
Hamiltonian?
because we have to calculate the probability after some time t. So we will evolve this linear combination state now.
Okay, okay.
Yeah. So now, so these things like for the sake of clarification, uh, we have discussed it, but not needed, not relevant here. So this is the initial step, which is in the uh, I mean the eigenstate of uh, Sy operator. So now like we have to calculate. So let's n uh, we have to know what is this C1 C2 value. So C1 is basically something like, as usual you can write it like you can calculate 5 on acting on plus. So Phi 1 you can write it as like phi 1 I, as I like told you right here. So this is your phi 1, and this is your phi 1, and this is your phi 2. So we have to take conjugate of phi 1, that is 1 by root 2 1 minus I, and then plus is given as 1 0 1 0. So that means you will get here 1 by root 2. Similarly, if you do C2 phi 1 plus, then that is 1 by root 2 1 plus I 1 0. So that that will be 1 by root 2. So so now here, uh, so again, so finally the initial state, the complete form of initial state is this 1 by root 2 phi 1 plus 1 by root 2 phi 2. Phi 1 phi 2 are your eigenstates of S1. And then when you write after some time t, if you would write this uh, the state of the system, it will basically evolve. So again, like we know to evolve, we usually write for the this will be minus I h bar t phi 1 plus 1 by root 2. So this will be I e1 e1 I by h bar e2 t phi 2. So again, like this is something I have like we have been doing even in our previous discussions of this tutorial session, that like when we have some state, like since if we have a state like psi equal to c1 phi 1 plus c2 phi 2, and this state is some, this is at initially, and when you evolve this at some time t, you basically operate ht on psi 0. So that means you at on c1 phi 1 and so on, you will get c1 minus I e1 over h bar t phi 1, and you get the other term the same way. So that is again, like in that aspect, we have estimated what is psi t for the given Hamiltonian. So now we know the psi t. Now we can further write 1 by root 2 uh, e to the power where e1 is given uh, so so your uh, so what will be your e1 here is so your uh, so your E1 is your, since your Hamiltonian is omega sy, so the E1 and E2 are basically your eigenvalues of sy. So the eigenvalues of sy, like as it is like given here. So for sy, these are the h bar by 2 minus h bar by 2, your eigenvalues. So so now even here, what I was telling here, this E1 is your eigenvalue. So if h is acting on phi 1, then this will be E1 will be your eigenvalue corresponding to phi 1. So that is how this when H on phi 1 that gives this uh, E1. So same way, like here we have h equals to omega sy. So when that acts on the phi 1, then it will give omega times the eigenvalue of sy when acts on phi 1. So that is like I can write this as uh, minus I e1 is given right here. So that will be e1 is uh, minus h bar omega by 2. So that is uh, minus minus will become plus, so that is I omega t by 2 phi 1 plus 1 by root 2 e to the power minus I omega t by 2 phi 2. So so this becomes your final form of your uh, psi t. So you have this psi t. Now we have to calculate what is the probability, or let me write this even further, like you can so side t side t I can write further as uh, 1 by root 2 uh, e to the power omega t by 2 uh, 1 by root 2 iota by root 2. So the I'm replacing phi 1 phi 2 the column vectors which I showed you before. For that is the those are the eigenvectors of your sy. So sin omega t by 2 and phi 2 is 1 by root 2 minus I by root 2. So that means psi t is 1 by 2 is your overall factor you have uh, e to the power uh, I omega t by 2, and here you have I omega t by 2. Same way you have overall factor of half with the minus I omega t by 2 and minus I omega t by 2. Now like I can write this side t, if you see, as cos of omega t by 2 and sine of omega t by 2. Since e I omega t plus e minus omega t by 2 is cos of omega t. So these are your Euler's relation. So I hope you are familiar with this. Uh, by 2y is sine omega t. So this this is your psi of t. So finally you got your form of psi of t. So initially your psi 0 was some plus state. So that was 1 0. After time evolution, after time t, so you have psi t, that is cos omega t sine omega t. So uh, so uh, I think there will be a negative sign here, a relative sign of minus sign here. So because this is I have like uh, did a small mistake right here, so this will be negative. So then in the question it is given like when you measure SZ, when you measure SZ, what is the probability? What is probability of getting? I think it was minus h bar by 2 was given. Minus h bar by 2. So so if minus s bar by 2, like what is the chance that you will get the eigenvalue minus s bar by 2? So minus s bar by 2, like is the eigenvalue of sz operator when your eigenstate is uh, uh, minus, that is 0 1, because plus is some we denote it by 1 0. This eigenvalue is lambda of plus is h bar by 2, and lambda of minus is minus h bar by 2. So minus h bar by 2 is asked, so that means we uh, that means the final state after when you measure sz will be minus. So that means we to get the probability we have to act minus with minus with the psi of t. So that is the probability after time t. Uh, this in a product square will be there. So that means you have minus is 0 1, which you take its transpose, and you have cos of omega t and minus sine omega t by 2, omega t by 2. You take the inner product square, that is, and that will give you sine square omega t by 2. So yeah, and this is your probability. So like, did you get this, or like do you have any?
Hello.
Ah, yeah.
So yes, it is okay. But after the time evolution,
Uh-huh.
in the matrix we have cos omega divided by 2 minus
Right.
sin omega divided by 2. So after the time evolution, it is not necessary to retain it any basis. Yeah, because now
Uh,
it has no basis.
no, like after time evolution, like I wrote it in matrix form because at the end, like I have to take the inner product with this. I mean, I have to take the inner product at the end with this 0 1, because 0 1 I know that because what is asked in the question, what is the probability that after you measure, or what is the probability that when you measure psi t, when you measure this psi t, that you will get uh, uh, like when you measure psi t, that you will get this minus. So that means you have to take the inner product of minus and psi t, and this minus state I know it's matrix form. So if I would write the form of psi t is also in matrix form, then I can take the inner product. If I know the some like some kind of functional form or some other like yeah, some sort of uh, functional form of psi t and minus, then I can just do a inner product. Like if we know some functional form, then we basically do this overlap integral. That is the
Okay.
equivalent of doing inner product in functional basis. But right now, like we have matrices because everything we are expressing here in terms of matrices, and also like it is not something in some kind of eigenstate inner product that we are doing, because uh, like if we have something 5 to 5 1, then it would be some orthogonal, we know that it would be either 0 or 1. So it is not in that like proper eigenstate relation. So we need to uh, have this in matrix form.
So also the form of the probability is that, say physically, it means that half of the time it will be 0 1 state, and half of the time it will be plus eigen state, and half of the time it will be minus eigen states.
Uh,
This sinus square omega divided by two.
so this means that like your the state that like this means that like when you are measuring psi t and you're getting negative, and its probability is sine square omega t by 2, that means the probability will oscillate.
Yes.
So it would at some point it would be like the chance of getting this state would be zero, and at some point it would be the chance would be very high. So basically, if you plot this sine omega t, you get something uh, like when you plot the sine square omega t, like so like I, you get some kind of this kind of oscillatory pattern. It, it do not have any this negative part because this is sine square. So at one like so let's say this is your time axis. So and at some time yeah let's say you are measuring it initially. So initially the state was at some state this, so there is no chance of getting uh, this minus state because uh, at t equal to 0, this you cannot have this because t equal to 0 you have uh, psi t equal to 0, you have plus. So the probability of getting minus at t equal to 0 is 0. So, but when you move, let's say when you calculate this time period, like at this will be some, let's say t by 2. If it's this is t and this t by 2, at this t by 2, the probability of getting this minus state will be high because that is the maximum value probability. So at every equal intervals of t, like you will find after again after t you will have this 3t by 2, you will again find the probability of getting this minus state would be high again. And same way like this probability value of this getting getting this state, probability of getting minus state is oscillatory. So in time t. So at some time it will give you maximum value, at some time it will give you zero. So this will be keep on repeating.
Okay. So as this problem discussed that initially your Hamiltonian is in the y basis,
Right.
SY basis.
Uh,
So for example, you have a Hamiltonian which is a combination of SY and SX.
right. Yeah.
It can be, it can be.
Mm-hmm. Hmm.
Then you have to write down the Hamiltonian as a linear combination of these two,
Yeah. You have
uh,
to. Yeah. Yeah.
SY and SX. Yes.
Yeah. Sy and Sx. So
Okay.
because you have uh, you have both the like operators sy and sx, so whatever the state it would be of your Hamiltonian, that would be that must be related to your both sx and xy.
So the procedure is same, the calculation part is same, but you have to write down the Hamiltonian in the correct basis.
Yeah, yeah. So, that would be a bit like complicated case, but there are things like you can always calculate that. Yeah, but that would be in linear combination. So, like you have to start from the linear combination of some sy and sx, and uh, it depends on like what is the question. If the question is given in some other uh, like uh, for example, the eigenstate is something that is not known when you have sx or sy together. So to get the eigenstate, what you can do, like you put the matrices like the sx xy matrices which is given here, and then calculate the eigenstate of that entire matrix. So Instead, like we could have also solved this question, like we know omega h equals to uh, yeah, omega sy, and if we do not know like omega, yeah, omega sy, and sy as I showed you earlier, that sy is your this matrix. uh, yeah, sy is your this matrix. So you put this matrix and take its that, yeah, that is what's the same thing, only we did it like you put this sy matrix and take its eigenstate. So its eigenstate would be this eigenstate would be this. The same thing you would also do if you have some other Hamilton. You take the complete matrix form of Hamilton and take its eigenvalue and eigenvectors.
Okay.
So yeah, so here we had this like 0 I. Oh no, that was not the matrix. I think it was this matrix. So yeah, that is you'll do. So now, like yeah, like was it clear or like anything more?
My question was that suppose your Hamilton has written something omega sy plus omega sx.
Mm-hmm.
So there is a combination of sy and sx.
Yeah, yeah, yeah. It would be
So
like the eigenstate has to be some linear combination of the both two.
okay, okay, okay.
I mean, because you have S1 and S6, both the states are there, so that means like both the eigenstate will contribute.
Okay.
But I'm not saying like, I mean, it can be in the eigenstate of Sx as well. For example, like initially in this question, the Hamiltonian was in plus state, so that plus state is the eigenstate of Sz. But that
Yes.
Sz is some linear combination of Sy eigenstates.
Yes.
So there also, like if you have a Hamiltonian Sy plus Sx, your Hamiltonian can be, I mean, the eigenstate corresponding to the Hamiltonian has to be some linear combination of Sy and Sx. But
Yes.
the,
I
the
am also
some state, it can be in some state which could be only the eigenstate of Sy, or could be the only eigenstate of Sx. It can stay in that, but or the complete eigenstate of that Hamiltonian will be some linear combination of this. Yeah.
so whatever your Hamilton will be given. Say in this problem,
Hmm.
you add omega sy plus omega sx. Say for example.
Uh,
So now you have to and your initial state is minus state in the eigenvector of z.
mm-hmm.
So now we have to write down the Hamiltonian, sorry, the initial state in the eigenstate of Sx and Sy.
Yeah,
Then you
yeah,
do the same way the
yeah,
calculation. Yeah.
yeah, yeah. Yes, yes, yes.
Yes. Thank you.
So when you have Sx and Xy, so like there is this way to do it. Like when you directly do the Sx and Xy, it would be a bit complicated to do. So what you can do, like you can express S, like let's say some omega 1 Sx and omega 2 Sy. Then you can just simply, it's a good way to do it, like you express Sx as some half of S plus S minus, and Sy is half of, or 1 by 1 S plus minus S minus. So when you write this way, Sx and Sy, so your Hamiltonian will be in terms of S plus and S minus, and this S plus and S minus will be easy to calculate probabilities and or any expectation value, or like anything, or I mean expectation value of energy or something, if you want to calculate at the end of the day, because this S plus S minus uh, are basically just I mean like their action on this SZ eigenstate, like let's say plus or minus, like it will be zero when you operate this between S plus or minus, then it will give h bar by 2 plus something this. So so you know the action of this S plus and S minus. So and that would be easy to like calculate your probabilities and or other quantities. You do not don't have to use any, I mean, this matrix form and eigenvalues, so you can directly do that way. So that is like that could avoid uh, quite a lot of complication. Maybe I think which you may face it when you have this only s plus and s minus. When you have only sx and xy operators in the Hamiltonian, you don't convert it to s plus and s minus.
Okay.
Yeah, that is like good way to think about like how you can be assured that like what would be your form of your eigenstates and I mean of your Hamiltonian when you have both sx and xy.
Okay.
Yeah. So like I had some like, more couple of questions, but since I think like we are running out of time, so like it's also uh, already 6, so maybe uh, like we can stop here and uh, if possible we can like, discuss them in the next time in the next week session and uh,
So
yeah.
we will get the next part in the website.
Sorry.
We will get this the discussion of the next part in the website, in the course
Next
website.
next part, you
Uh,
mean like next week again we will meet live, like how we had this. Uh, this is your week 3 tutorial session.
okay.
Like there will be again a week 4 tutorial session, like which will
Okay.
take place next week. So if possible, like I can discuss one or two more similar questions like this again next time during the week 4 problems solving session, or also like any other doubts that you might have, like we can also discuss them. So but for now, like everything clear, or is there something more you want to know, like?
No, it's okay.
Okay, so
But we will get the recording. Yeah.
yeah, you will have the recording. Like I think you will get the recordings and the materials that which
Okay.
I was working on. So that would be also shared with you. Like I think that is already shared with you in your NPTEL portal. You can check them out. Like
Okay.
I
Okay.
mean,
Thank you.
today's material will be shared like soon by tonight or maybe by tomorrow. Like most probably by tonight. Like.
Okay. Thank you.
Yeah. Okay. So thank you. So, so if there's no more question or no more like comments or some uh, queries, then we can stop here. Like,
So uh,
yeah,
I have one thing,
yeah.
because there is a parallel session going on the same course. It is
Oh,
the same assignment.
no, no. I think that session would be like discussing on some other uh, questions or other problems. I'm not sure,
Oh,
but like what I am doing mostly, like I try to like solve questions which is quite more relevant to the respective week's assignment. For example, for week 3 assignment, you will find most related to this angular momentum spin
okay,
algebra and other problems related to it. So I have also thought of discussing these problems, like something relevant to this kind of problems to you, so that like it can help you in some way to solve your assignments and yeah, and also in understanding the concepts.
okay. Thank you.
Okay, so if there's no more queries, then we can end it here. So yeah, so bye. So meet again next time.